Hi! Now that we have introduced the notion of functions of several variables and seen how we can globally consider them, let's get a little more analytic. When we considered functions of a single variable, we saw that many interesting qualities had to do with the rate of change of that function. This rate of change was most adequately represented in terms of the derivative of the function, and graphically corresponded to the slope. We will see that the topic of differentiation is a bit more complex in the case of several variables, but I am sure you will master it as well as the single variable case. The reason for the complexity is because the rate of change of the function depends on the direction we consider. In the single variable case, there is only a positive direction where x increases and a negative direction where x decreases. But in the case of two variables x and y, there are infinitely many options. We can have both x and y increase along the line where y equals 2x, for instance. And in that case, the rate of change could be different than if we let them both increase along the line where y equals x. We can still describe the rate of change as the slope of the graph of the function, but clearly this slope can depend wildly on the direction we consider. We will fully deal with this problem in the next week of the course. But for now we can already consider a partial resolution that is both practically and theoretically important. Consider, for instance, the example of the dependency of the volume of an ideal gas on the pressure and temperature. We might then be in the situation where we can somehow regulate the temperature. In particular, we might be able to keep the temperature at a constant value T0. Essentially, this means that the volume becomes a function of just the pressure, and we may consider its rate of change as a function of this one variable. Of course, we may similarly consider a situation in which we are able to regulate the pressure and keep this at some constant value P0. This would mean the volume becomes a function of just the temperature, and again we may consider the rate of change of this function. What we have just described is the idea of so-called partial derivatives. In short, a function of two variables has a partial derivative with respect to each of those two variables, and they are the derivatives of the functions of one variable one would obtain if the other variable actually remained constant. Hopefully it is clear how this notion would be generalized to functions of more than two variables. In essence, this doesn't change matters much, except that now we must hold more than one variable constant when considering the partial derivative. The definition here is in terms of the derivative of a function of one variable. If we consider then the definition of the derivative of a function of one variable in terms of limits, we find the formula shown on the slide. In particular, the quotient appearing in the definition for the partial derivative with respect to x has a step size h in the denominator and the difference in function value as we take a step in the x direction in the numerator. We then take the limit as the step size goes to 0. The definition for the partial derivative with respect to y is, of course, similar. Note, by the way, that we will not in general be using this definition in terms of limits to actually compute partial derivatives. Instead, we will rely on already knowing how to differentiate many functions of a single variable. However, the definition in terms of limit does make one thing clear, namely that, as is always the case with limits, the partial derivatives need not exist. In particular, when the function is discontinuous or overly choppy or spiky in the x or y direction, the relevant partial derivative will fail to exist. Before having a look at some examples, let's fix some notation. As you can see, there are plenty of options. We will mostly stick with the first option, where we indicate the partial derivative of a function at a particular point by using a subscript of the relevant variable. Sometimes we will also use the notation with the del symbol indicated on the slide. Note that this is in particular not a d and also not a delta. In particular, there's a difference between the so-called total derivative, indicated by the letter d, and the partial derivative, indicated by the symbol del. Now, let's consider the following three examples of partial derivatives. First of all, we consider the function for the volume given by the ideal gas law. To take the partial derivative with respect to the pressure, we should consider the function obtained by plugging in some value T0 for temperature and then taking the derivative of the function so obtained with respect to P. Pause the video and give it a try before we consider the answer. Indeed, the partial derivative with respect to pressure at the point T0, P0 is given by negative n times r times T0 divided by P0 squared. This is simply because the derivative of 1 over P is given by negative 1 over P squared. Similarly, we may consider the partial derivative with respect to temperature by plugging in P0 and taking the derivative with respect to temperature. For each example, try to pause the video and see if you compute the answer beforehand. Indeed, the partial derivative with respect to temperature at the point P0, T0 is given by n times r divided by P0. Let's consider this next example of a function of 3 variables. Let's consider all derivatives at once. Again, pause the video to try it yourself first. Indeed, the partial derivative with respect to x at the point x0, y0, z0 is as indicated on the slide, because if we keep y and z constant, we simply end up with some constants times x, and its derivative is just that constant. For the partial derivative with respect to y, we see that we only get a part coming from the first summand, since the second summand doesn't depend on y, but only on x and z. And so its derivative with respect to y is 0. Finally, note that for the partial derivative with respect to z, the same is true for the first summand, which only depends on x and y, but not on z. Also note that there we have needed to apply the product rule. For instance, if we want to know the partial derivative at the point 1, 2, 3, we find the value as indicated on the slide. Let's try one final example to top things off. Let's compute both partial derivatives of the function g given on the slide in the point where x0 is pi over 6 and y0 is 0. Again, pause the video and try to find the values yourself. Indeed, the derivative with respect to x is simply given by negative a half, since we get the derivative of the cosine, which is negative sine of x times 1 plus the absolute value of y. Since the absolute value of y is 0 and the sine of pi over 6 is a half, we find negative 1 times a half, which is negative a half. However, for the derivative with respect to y, we must actually conclude that it doesn't exist. Indeed, if we plug in x equal to pi over 6, we find the function absolute value of y plus 1 times half times square root of 3. But the absolute value of y is not differentiable with respect to y, since it is too spiky at the origin. In particular, for negative values, the derivative is minus 1, and for positive values, it is 1. But at the origin, these two do not match. As mentioned earlier, it is possible for partial derivatives to fail to exist, as is the case here. As you can see, it is possible for either one or both of the partial derivatives to fail to exist. The exercises will quickly help you get proficient at computing these partial derivatives, but perhaps it is a good idea to consider once more what we are actually computing. In particular, what does it mean graphically to consider the function obtained by fixing the value of one of the variables and then taking the derivative? Well, this is really explained quite clearly by considering what it means to fix one of the two variables at all. When we consider the graph of a function of two variables and we fix one of the two variables to a particular value, we are looking at all points on the graph that also lie in a particular vertical plane, as you can see on the slide. This intersection gives us a curve in that vertical plane, which we then interpret as the graph of a function of the remaining variable. The partial derivative is the derivative of this function of one variable, and so it gives the slope of this graph. So we may interpret the partial derivative with respect to x as the slope of the curve given by intersecting the graph by the vertical plane that is parallel to the x-axis. And similarly, we may interpret the partial derivative with respect to y as the slope of the curve given by intersecting the graph with the vertical plane that is parallel to the y-axis. Finally, let's consider what happens when we vary the point at which we take partial derivatives. If we have a look at the expression we obtained for the second example, we consider before we plugged in the point 1, 2, 3. We see that we could have plugged in any values x0, y0, z0 in these partial derivatives. And so in particular, the partial derivatives themselves are again functions of several variables. This is of course similar to the situation for a single variable, where the derivative of a function is again a function. Just so, we find that the partial derivatives of a function of several variables are again functions of several variables. Our notation for these functions is, as you can see on the slide, a natural consequence of the notation we saw earlier. Partial differentiation is a core skill in calculus of several variables, and you should be able to do it relatively effortlessly with sufficient practice. To get started, consider the following function of 3 variables and see if you can determine its partial derivatives with respect to each variable. In the text below this video, you can find a worked out solution. Of course, make sure to also practice using all the other exercises with this lesson.